Um, Welcome, Matthew, and you can start your presentation now. Thank you.
Cool, thanks, Marta, and yeah, thanks everyone for coming. It's great that we've got a bit of a crowd. I said to Marta last time I joined for a paper discussion that it's great to have the opportunity to talk about these issues, especially given that they're potentially controversial. You know, I probably am going to step on some people's toes. I'm aware of that. Going to be some shots fired. But hopefully also it's going to provoke discussion and hopefully give us an opportunity to think about how we can improve our research practice as well. So the title of my talk is, well, maybe I should just say who I am first. So I'm a researcher in artificial intelligence and machine learning in computer vision, Center for Vision, Speech and Signal Processing at the University of Surrey. And I'm also a lecturer in the Institute of Sound Recording, also at Surrey. But I've got, you know, relatively diverse interests, so it's sort of taken me through psychology, etc. Yeah, that's sort of what brought me here today. So the title of the talk is Prediction and Causality, Either, Both, or Neither. This is a bit of a rhetorical title. It's a question that's supposed to maybe ask psychologists whether or not they're undertaking primarily predictive work, primarily causal work, or maybe neither, maybe a mixture of both, maybe a conflation of both. And this relates not just to their approach, but also their hypotheses and the models that they use, their statistical models. So as Marta said, this is based on a paper called Limited Functional Form Misspecification and Unreliable Interpretations in Psychology and Social Science. The paper's quite long. It's upwards of 12,000 words, and I wanted it to be longer as well. It's a little bit of a sort of an opinion piece for me and a sort of labor of love. It's still in progress, and I'm still adding to it. But I've had to pick out some of the more juicy parts for this talk, and obviously we've got limited time, so I tried to pick the things that are potentially, in my opinion, maybe more important, but it was hard. So yeah, if you want to know more, then certainly feel free to check out the paper. So the key messages to take away, I guess, from today is that typical models have limited functional form and typical models are causally misspecified. By typical model, I mean the vast majority of models being used in research in psychology and social science. Of course, there are some models that are very sophisticated, very comprehensive, very interesting, very novel and flexible models. But the vast majority sort of fall into these broad categories that we're all familiar with, like linear regression, for instance. By functional form, I'm going to talk about that later on, but principally it relates to the fact that most of our models are linear, so we're sticking to straight lines or low order polynomials through everything. And typical models are also causally misspecified, so causal misspecification will come on to later, but it relates to this mismatch between the true data generating process and the structure of the model that we're using. And the consequence is that actually most of the models in psychology are relatively poor predictive models, and they're also poor causal models. As we'll talk about, there isn't much causal inference, at least explicit causal inference in psychology, but despite that, there's still this overlap which we need to be aware of. And the result of all this is that most of our interpretations are somewhat unreliable and conflated. So conflated in the sense as a mixture of this prediction and causal language, terminology, our intentions and our approach versus our model and so on. So I've caricatured the research pipeline here at the bottom. And I had a separate version with all these interconnecting lines. I think when we're planning our research, we should consider every part of the research very holistically. And you'll see that at various stages, we have the opportunity to choose between a causal or associational, and I'm using the word associational synonymously with predictive. We've got this opportunity to choose one or the other. I've said theory is probably causal. I mean, in science, I think we're primarily interested in causal questions. Predictive questions are potentially useful to us. Predicting when something will happen can be useful, but it doesn't help us understand the phenomenon. So I think I've sort of hazarded that maybe this is going to be causal, and then we have the opportunity to choose later on whether we're going to, regress is an overloaded word, but fall back on a predictive technique in order to answer something about this theory or test something about it. So just as an example, of how this sort of manifests. I've always just zoom in on this sort of smaller region of this pipeline here. Just look at this, where we've got some data and we've got an analysis and we perform some interpretation. Let's say our analysis is multiple linear regression. This is the normal kind of multiple linear regression where we've stuck in some variables. These variables are probably justified on the basis of some theoretical notions, maybe relationships, but also maybe on some predictive heuristics like bivariate correlations, or maybe we've used, say, a forward-backward method for variable inclusion, so on and so on. So this becomes a predictive or associational or correlational model. And I think we're fairly okay with, that's not too shocking. And it helps us maybe tell us what co-occurs, what is likely to occur, what is linked with, and so on, associations between these variables. Actually, multiple linear regression is a causal model, and I've said it's a causal model in disguise. Not many people treat multiple regression as a causal model, but I think it's very important that we understand that it is a causal model. And the result is that when we're using it in a predictive sense, such that we're not really considering the true causal model, the true causal relationships in the data, there's a mismatch between the two. And this yields completely arbitrary significance levels, completely arbitrary direction, so positive or negative, and completely arbitrary magnitude. So this is an instance of misspecification, really, and that's the thing that I want to spend more time on today. But there is also the added issue of the fact that this is a linear model, and actually very few things in the world behave linearly. But this issue of causal misspecification, essentially it boils down to the fact that the structure of the world, the true sort of causal mechanisms underlying our observations in the world, interact with the imposition of the structure in our model. So this is the interaction between the model and the data, essentially. So there's the adage, when something's like not that complicated, you tend to say, oh, it's not rocket science. And so I'm going to say social science is not rocket science, but actually it's a lot harder than rocket science. I think, we've made a lot of progress sending rockets up into space, despite actually not putting that much time into it. There was a brief sort of spurt earlier on last century, but then we've only sort of started doing it properly recently in anger. But we've made tremendous progress, and it's actually quite difficult to send a rocket up into space. There's a lot of stuff to consider, a lot of variables to account for, a lot of uncertainty. But actually, in comparison, the systems that we're dealing with in society are very much more complex. And it's interesting to note that we tend to deal with all of them using straight lines. So I think that the tools and the analytical tools that we're equipped with are insufficient to deal with the complexity of the problem. So today, this is a brief overview. I'm going to just briefly go over the background. We all know what the replication crisis is, but I'm just going to talk about it just to contextualize everything, talk about some of the issues that relate to what I'm talking about today, and then I'm going to go on to functional form. So what functional form is, how does it relate to predictive modeling, why are the current models that we use limited in this functional form, and what are the alternatives, how can we improve on our functional form. Then I'm going to go into causal modeling. I'm not going to talk about causal inference. It's a massive field. It's very interesting. I think that it's quite accessible. At least the introduction is quite accessible. There's a lot of great courses now. But I'm primarily looking at it from this perspective of the imposition of structure. And this is probably a misspecified imposition of structure. And it doesn't matter whether we're undertaking predictive modeling or actually doing causal inference. This imposition of structure will have an impact. And so this relates to misspecification, how we deal with this misspecification, and what it does to our interpretations and our results. How do we interpret those effect sizes that we get out? I did actually have this section, I've removed it, explanation versus interpretation. I think it's very useful to distinguish between explanation and interpretation. These are two different things. In psychology, we tend to just do interpretation, but that's somewhat inappropriate in many circumstances. But unfortunately, I can't talk about that very much today. And then I'll come back to, I'll summarize everything and I'll actually talk about some recommendations for improving practice at the end. I think it can be all very depressing when you think about all these issues, but hopefully we have the opportunity to improve practice. So moving on to the background then, there are loads of shocking statistics about the replicability rates. We are probably familiar with quite a lot of that research and that literature. It's a vast literature that is ever growing. Again, it makes us want to, give up, go home and cry. And as I'm going to sort of convey to you, I think it's actually worse than any of us actually think, which is even more worrying. But this was an extract from my paper. It's just the tip of the iceberg in terms of the literature, but obviously there are issues associated with misunderstandings of p-values, of statistical tests, measurement problems, a lack of meta-analysis, warped interpretations, a failure to account for non-ergodicity and aggregation, low sample sizes, pressure to publish, and so on and so on. Again, just the tip of the iceberg. It's all very, very concerning. There are some issues that overlap with what we're talking about today. and these are conflation with terminology and language, the conflation of predictive and causal language. Gross did a review of some papers and concluded that some parts of the articles read as if the entire endeavor were non-causal, yet other parts make sense only in the context of answering causal research questions. I think this is very interesting. I see papers coming out almost weekly where there's some conflation going on in sort of consecutive sentences, where they might use causal language in one sentence and then sort of predictive or associational language in the next sentence. And even though we tend to get drilled into our heads that correlation is not causation, I think there's still a lack of clarity when it comes to what language we should be using in our research. For instance, there was a paper recently on residential green space and the impact on child development. And I say impact, you know, that's a causal statement. If something impacts something else, they use the word benefits. So again, a causal statement. But then in sort of consecutive sentences, they would use the word associated with. So they weren't clear in themselves whether this was causal research or not, or at least they weren't demonstrating they were clear in the language. And the second issue that relates to this is the conflation between the approach itself, so you know, the hypothesis, what we want to do with our research, and then the model being used. So Galich Shmueli said the type of statistical models used for testing causal hypotheses in the social sciences are almost always predictive models. So this is sort of speaking to the fact that we have these causal theories. We're interested as scientists in causal relationships and causal questions. And we may even let that bleed into our hypotheses and what we're going to test for our research. But then when it comes down to it, we end up falling back on a predictive model. And unfortunately, predictive models, there is a fundamental semantic gap between a predictive model and being able to answer a causal question. There is just a gap there that you cannot bridge without some leap of logic. And it's going to limit us if all we're doing is predictive modeling. So there's some discussion about why this conflation occurs. Where's this misunderstanding? What's going on? Hernan refers to causality as the C word. I'm sure we all know a slightly more rude C word than causality, but he's demonstrating the fact that there is this taboo around causality and we perceive it or equate it to something rude that we shouldn't be doing in our research. And Dowd said that causality, the literature on causal inference must be one of the oddest literatures in all of academia, and Gross referred to the causal inference as a taboo. So we do get routinely discouraged from undertaking causal inference in psychology and social science. I think this is particularly true, obviously, in the non-experimental sense, and that's primarily what I'm considering today. We make some observations, we collect some data, but these are non-experimental conditions, and then we're trying to deduce something scientific, i.e. causal, about those relationships. And we are discouraged from doing that. And I think the result is that actually there's very little causal inference being done in psychology that's non-experimental. So there's a tweet recently that I saw that I thought I'd put in here. Someone asked Udair Pearl, who's I guess the world leading expert in causal inference, certainly the most well known, what is the statistical test to establish that event B is caused by event A? And Pearl simply replied, there isn't any. So the idea here is that statistics is separate from causal inference. In statistics, we're concerned with things like probabilities, likelihoods, expectations, conditional expectations, Y given X. But these are not causal quantities. These are simply probabilities, likelihoods of things occurring or co-occurring with something else. And causal inference is really concerned with taking these statistical quantities and manipulating them in such a way that we can derive causal estimates. We have some desired causal estimand, and we want to be able to translate a statistic into that causal estimate. And these causal questions are the most important for us as scientists. They help us answer how, why, what if, underlying mechanisms that led to the observations that we've collected. And whilst prediction is still useful, it's got a very much different scope, a much more limited scope in terms of answering questions like when something's going to happen, which thing might happen in terms of a classification, or maybe by how much in terms of a regression. So again, there is a fundamental gap between prediction and causality. So as part of the background, I checked out what the most common methods are in psychology, and this was quite disappointing to me. The top three methods were regression, multiple linear regression, for instance, structural equation modeling, and measures of association like Pearson's correlation coefficient. So the thing that struck me here is that there are no good predictive models in this list. So it might sort of suggest that maybe we're not interested in prediction, but then of course these models are predictive models, these associated models, they're just not very good. So we must be doing presumably something very clever with these models, right? We must be doing a lot of feature engineering. We must be sort of projecting our nonlinear relationships into a linear manifold and then using our linear models. Well, unfortunately, I don't think that's the case. I think if you were to confront most professors in psychology with the notion of projective manifolds, I don't think they would really follow what was about. There is structural equation modeling on here, which made me think, okay, they're doing explicit causal inference then, because structural equation modeling is a causal inference technique. It allows you to impose explicit causal relationships. But actually, when you look at the literature, no one's really using it in a causal sense. It's just the graph is imposed. It's assumed to be valid a priori, and then it's not really validated. There's no causal discovery there. It's just used and then interpreted primarily predictively. So there's this weird mixture of not very good predictive models and then explicit causal models that are interpreted predictively, and never validated in terms of their causal structure. And I was just like, okay, this is actually quite a lot more serious than a lot of the other issues that have been mentioned in the literature. And if we go back to our pipeline here for the research pipeline, it feels to me that if you don't understand a p-value, obviously that's a problem. And if you don't understand statistical power, that is also a problem. But let's say we get to our interpretation stage at the bottom left here, and we're confronted with a p-value that we don't quite understand, and maybe we overinterpret it. Maybe it's like 0.04 and we're saying, yeah, look, we found a really good effect here. Maybe that's not great, but if our model is fundamentally wrong and that p-value is just not meaningful, I think that's a more fundamental issue. So even though I'm not trying to minimize or distract away from these other issues, I think there are more fundamental problems going on. And I think there's this sort of circularity to the fact that no one really knows about these other techniques. So when it comes to peer review, you just get the same people saying, yeah, you've ticked the box and that's fine. And unfortunately, we're not going to make progress scientifically in that way because of this, well, amongst other things, fundamental gap between this predictive modeling and causal inference. We're not really going to make scientific progress in understanding the phenomena that we're interested in. So in summary, for this background, there are loads of problems with research. It's worse than even you might think, even given the vast literature in the replication crisis. And as I said, many of these issues are fairly top level. They assume that a lot of the more fundamental aspects are sound. And there's this conflation between prediction and causality, both in terms of the language and the models. Maybe this is due to a taboo around causal inference, or maybe it's due to a lack of understanding. I think it might be a bit of both. There's not many predictive techniques. We've seen that there's linear regression, correlation. So actually good predictive techniques are comparatively rare. And even though there's explicit causal SEM being used, it's not actually being used in a causal way, which is a very strange situation. So that's the end of the background. And the first thing I want to talk about, which is not really the meat, but it is the appetizer, I suppose, is the issue of functional form and why that affects us and why we have limited functional form. We know this equation here, y equals ax, and essentially functional form is just the mathematical form describing the relationships between the model variables. So this is a linear functional form because any change in x results in a linear change in y. We can incorporate more variables, that's all fine. And even when we start including these nonlinearities here, like x squared, these are what I would call features of the original variables, or sort of subfunctions. And so this is still a linear equation. We've now just got the relationship between x squared and y is linear. And so, you could actually extend that logic ad infinitum to the point where you could actually have almost any function substituted here as a feature of x, and you could still call it a linear equation. And that's what sort of Taylor expansion does when we sort of approximate a function as a linear sum. And you can extend that infinitely, and everything becomes a linear model. But primarily what I want to talk about and use the word linear to describe is that actually the standard linear models in psychology and social science, which are low order polynomial terms at best. If we've had a lot of coffee that day, we might use an x cubed, but otherwise we're generally with x to the 1 or x to the 2. And these themselves are very sort of quantized polynomials. We're not exploring, say, x to the 2.3 or something like that. We're just sticking with these low order polynomial terms, and we're saying they are sufficient for our toolbox. Now, there are very few social phenomena that actually have linear mechanisms. I honestly can't think of one that's really linear and would be sensible to describe as linear. I think a lot of social phenomena are actually incredibly complicated, incredibly dynamic, and very nonlinear. Just for a start, there's obviously saturation effects that render any sort of indefinite increase, linear increase, impossible. And yet we almost exclusively use linear models. And I would like to ask sort of rhetorically, but maybe try and offer some of my own hypotheses for why this is the case. Why do we always use linear models in psychology? Sometimes our data are limited. So fair enough, we don't have much data. Maybe it doesn't make sense to fit some hugely complicated function to it. I think this is an excuse. I think most people that use linear models, if they were to say to you, oh, we've only got, say, 500 data points. If you said, well, if I give you 5,000 data points, what method would you use? They would probably still say, I'll use a linear model. I just don't think that they have the tools and they're not equipped with the tools to actually use these, and they're not even aware of them. One of the other excuses that I see is our observations are sufficiently linear. Now, this for me is actually a little bit more acceptable. I think that quite often if you abstract yourself from a problem sufficiently, it might look like there's a linear relationship going on and you can sufficiently model it using a line. And I'm not actually proposing that we throw out linear models at all. I think there are good uses for them. I think limited functional form, maybe it's not always limited, maybe it's appropriate. And so I'm not arguing that we throw this all out. I'm just saying we should at least be aware of more appropriate techniques given the complexity of the phenomena that we're actually interested in. So just to kind of demonstrate some of these issues, when we're using, let me just get rid of something on my screen, okay. So correlation, for instance, very common, as we saw, correlation for modeling the supposed proxy for a dependence between variables. Obviously, it doesn't deal with nonlinearities at all. All of these have a correlation of 0. In the bottom right here, this is actually, there's no statistical dependence here. This is just a quad modal distribution. Over here, there is statistical dependence. This is a toroid or a circle. We've got the quadratic relationship here and a sinusoid. And if we use correlation locally, we can actually describe the dependence reasonably well. So if we fit a line to a small part of the covariate space here, we can model that increase in that sinusoid. But obviously, globally, it's completely useless. And when you think about it, correlation is a very, very blunt measure or proxy for statistical dependence. If you compare that against, say, mutual information, which is an information theoretic concept and quantity for measuring the actual statistical dependence between two variables, we actually get very reasonable outputs. So the mutual information between these two variables, x and y here, is nearly 0.8. We've got 0.99 for this quadratic and 0.4 for this toroid. So mutual information, I'm not going to go into the details of it, but it is quite commonly taught in engineering, especially in communications, is the Kullback-Leibler divergence between the joint distribution and the product of the marginal distributions, which might sound like a mouthful. Again, I can't really talk about it in detail here, but if you have questions at the end, maybe we can come back to it. But the point is that it deals with this issue. And so again, given that we're dealing with such nonlinear relationships, why are we not even aware of these alternatives? I find that mutual information is actually something that I get glazed eyes for in psychology. So the other problem with correlation, and correlation is just sort of like a subclass of generalized linear models, is that it is nonlinear in itself. So forget about the relationships between x and y for now. Correlation itself is nonlinear. And you can see that here, if you look at these top 4 graphs here, I increase correlation by 50%. So it goes from 0 to 0.5. I know it ranges from -1 to 1, but it's symmetric. So we increase it by 50%. And actually, there's not that much increase in visual dependence between these variables. And that's because it is nonlinear. As you increase it up to, say, 0.8 to 0.95, which is just a 15% increase, there is a much clearer visual change in dependence. And I haven't done anything funky with the axes here. This is just the nature of correlation. It is nonlinear. And so I guess the takeaway point from this is that if you're comparing two relationships, say we've got a correlation down at 0.2 and another correlation at 0.3, you're really comparing noise against a bit more noise. And I think it's very important that we understand these quirks to do with the measures that we're using. In contrast, mutual information, being the actual measure of statistical dependence between two variables, increases linearly with the increase in statistical dependence. So it goes from 0 up to 1.625 here. You can't indicate the slope with mutual information. It doesn't make sense to. It handles nonlinearity. It's just about statistical dependence. You can't have negative statistical dependence in that sense. But yeah, so I would argue that it's important to be aware of these limitations and quirks of the things that we're using. So all of these problems extend to linear regression more generally, the models that we're using. And so what can we do to improve on these issues? So first of all, you consider the alternatives like mutual information. You can consider using feature engineering, which most psychologists already do. So, we might be confronted with this quadratic here and say, that looks like a quadratic, I'm going to use x squared. I guess I would only warn against feature engineering to the extent that you are still imposing a function on this data that may or may not be correct or appropriate. It might be an approximation, it might not be quite there, and I've seen some pretty horrendous lines fit to data in peer-reviewed papers. So functional feature engineering is fine, and it does do the job, but it has to be done well, and it's actually quite challenging to do. So I'm going to recommend actually we extend our arsenal of analytical techniques to include more data-driven functional form approximation techniques from machine learning. This sinusoid with a linear trend, the blue lines that you might just be able to see underneath the original data, and the red crosses are a neural network. It's able to learn that function perfectly. It doesn't know that it's a sinusoid plus a linear trend, and obviously this is a very toy example, but if you fit a straight line through it, then obviously you just get that trend, and depending on where you stop sampling this sinusoid, that line will wave up and down over time, assuming this is over time. So there is a lot of opportunity for using more powerful function approximation techniques, and they get us much closer to the optimal functional form between our variables. But we do need to be aware of things like double dipping and overfitting. And this was one thing that shocked me quite a lot, actually, is that in psychology I was taught this, and it's also in some of the textbooks that I've got here. I was taught the forward and backward method for variable inclusion, but I was never taught in psychology anything about train test splitting or cross-validation. I know some people do use this, but it's not generally taught to psychologists. It's not generally used in psychology. But any data-driven decision process that you use to adjust your model will result in the inflation and undergeneralization of that model. So for instance, if you're looking at your data and your model and you're saying, if I include this variable, it's significant. If I include this variable, it's not significant. So I'm going to use that heuristic to decide which variables to include. You might even be doing it based off bivariate correlations, for instance, only including variables that are correlated with the outcome in a bivariate sense. These are all data-driven decision-making processes that need to be tested on an out-of-sample data set. And if you don't test them on an out-of-sample data set, you are literally overfitting your data. So it was quite a shock to me that I was actually getting taught to overfit my data, and it became less of a surprise that the replication crisis was kind of going on, given that actually it's actually taught almost as routine practice to overfit your data without doing cross-validation or train test splitting. So if you get into predictive modeling, say a lot of the techniques from machine learning, it'll be in the first chapter or maybe the second chapter about the bias variance trade-off and how you need to test on an out-of-sample data set. And this is true regardless of whether you're using a linear model or you're using neural network, gradient boosting machine, or random forest, for instance. So in summary, for the functional form section, there is a missed opportunity. We can certainly leverage a lot of techniques to improve on functional form. We need to become more familiar with predictive methods as a whole, being able to fit data, let the data speak, using Van der Laan's words, stop imposing this restrictive functional form when it's not necessary. And obviously, if we start doing that, we also have to understand the pitfalls associated with using these methods. They are more subject to overfitting than linear regression is, but actually the considerations still overlap with the use of linear regression. So we still need to understand overfitting, for instance. And we also have to understand the limitations. Whenever we're using a predictive model, we cannot answer fundamental scientific questions about why that phenomenon occurs, what the causal mechanisms are, and so on. So that predictive model will leverage anything it can to fit that predictive heuristic, whether it's ordinary least squares or ridge, whatever it is you're doing. And so I've drawn this bubble here to illustrate all possible realistic data distributions in the world, and maybe that's an infinite distribution, an infinite space. But traditional methods take up and can cover a very, very small portion of that space. If we use machine learning, we can expand, we can expand that bubble to cover more of that realistic data distribution space, but we're still not going to be able to reach this true distribution here. So that's obviously the target, to either have a class of models that overlaps with this or actually be able to directly model it. In reality, our models tend to be abstractions, so we might never model it perfectly, but we want to get as close as possible. So I think the first thing that we can do is explore machine learning techniques, for instance, to expand our arsenal of predictive techniques, but actually we're still not going to get quite where we want to be in terms of answering scientific questions. So in order to answer scientific questions, we need to consider the structure in the data. This is called a causal directed acyclic graph, or CDAG. It's a form of probabilistic graphical model, but if you're familiar with structural equation modeling, it's a bit like the visual representation that you use for structural equation modeling. These nodes are just variables, and these arrows indicate directional causal relationships. Usually you wouldn't include this one here, but the reason why I'm including it is because I want to communicate the fact that multiple linear regression is a causal model, and it's a causal model that has this structure. So you may hear people use the words independent variable. I would never use the term independent variable. Very rarely are our variables independent of each other. That was a very unique and ideal situation. But if your variables are, then you can call them independent variables, and this being your dependent variable. And you've got these causal relationships between the variables and the outcome here. And what I want to show you is that when we use multiple linear regression, we are imposing this causal structure. If the real world and our data really does correspond with this structure, then we can actually use multiple linear regression to obtain unbiased estimates of these true causal parameters here. So I'm going to demonstrate that here. This is written in Python. I was going to go through these code alongs during the talk, but I realize that probably most of you, if you do code, probably use R. And I couldn't be bothered to recode it, but it's very simple. It's very, very similar actually in R. So feel free to go back and run these yourselves. So I'm going to simulate data, 5,000 data points, just to get away from any issues relating to sample variance. I'm going to generate some variables. These are x1, x2, x3. These are all independent. Note they're just random normal Gaussian, mean 0, variance of 1. And the outcome I'm going to model just using some random coefficients here. So I've got 3.3 for the intercept, 0.1 for theta 1, 0.3 for theta 2, and 0.5 for theta 3. So these are just randomly picked just for the sake of demonstration. And I've generated this data. So I'm assuming that actually this is data that I've collected in the wild, in the world. And I'm going to see if I can use multiple linear regression to recover those true parameters, 3.3, 0.1, 0.3, and 0.5. So if I fit ordinary least squares, multiple linear regression, indeed, I get unbiased estimates for these. I get 3.3, 0.1, 0.3, and 0.5, which is very reassuring. I can use multiple linear regression to recover the true causal coefficients in my graph and in the real world. But this was actually only possible for two reasons. Firstly, everything was linear. We enforced that to begin with, just for the sake of demonstration. In the real world, obviously, we're going to deal with nonlinear complex relationships. But primarily it worked because the data generating process was just as trivial as the structure of multiple linear regression, and they matched. They were perfect, bang on matches. So if we stay linear, what happens if the data generating process, i.e. the real causal structure, increases in its complexity? So now we're assuming the real world behaves according to this graph here on the right. And if you're familiar with path diagrams, then you can calculate the effect of one variable on another just by multiplying these variables together. So for instance, if I want the effect of x0 on y, I just need to multiply -2 by -1 and I get 2. So the causal effect of x0 on y is 2, positive 2. And we're going to look at how we can recover that effect and see when we don't quite use the right technique, try and get a feel for how wrong our estimates are. So the equations here are the corresponding equations for this graph here. You don't have to worry about them. I've just put them up there for completeness. And I'm going to generate the data according to those equations. Again, you don't have to read through these at all. I just put there for completeness. And if you want to come back and run this yourself. And I've checked the bivariate correlations here. All of these variables are highly significant and highly correlated. So we've got correlations of 0.9, 0.76, -0.56, and so on. So if I were taking a sort of a usual psychology approach to this, it might be tempting to say, well, what we should do, given that all of these variables are highly correlated and they might even be theoretically justifiably related to the outcome variable y here, just include them all in the model. So that's one thing we can do. We can also maybe hazard what this graph actually looks like ourselves, even though this is the real graph. We don't have access to it in our research, but we could sort of try and figure out what these variables are and then decide which ones to include ourselves. So I'm just going to explore various routes for doing that. So recall that the true effect of x0 on y here is 2. And the first thing I'm going to do is just let's just regress y onto x naught. So I include y, I include x naught, I run a regression. The estimation for the effect is 1.28. So it's highly biased. You know, the sample size is 5,000. We're fine in terms of sample size. But the effect is incredibly biased. And if I had run significance, to do significance assessment, I'm sure this would be highly significant as well. So then we take the alternative approach, which is very common in psychology, which is to say all these variables are theoretically related, all of them are statistically related, you know, based on bivariate correlations. Let's include them all in our multiple regression and see what we get. Oops, we get minus 0.01. This may or may not be significant. I imagine it isn't, but it looks like a null effect to me. So you might do this research and you feel very dismayed because there is no relationship between x naught and y. This is a real shame. Maybe you can't get it published because, you know, journals don't like null effects and so on. So all very disappointing. You know, you should have maybe just included x naught and tried to get that published. But then probably some reviewer would have said, you should have included x4, x2, x3, x5, x6, x7, and x1. So, you know, you're sort of stuck behind between a rock and a hard place here. What if we include the mediator? Some of you probably know that you should include mediators in the correlation, in the regression. And indeed, if we do, we get this other weird result, which is actually negative now. So it's flipped in terms of its sign. So how do we move forward? What do we do? The rules for path diagrams are fairly straightforward. For causality, causal inference using directed acyclic graphs, they're very easy to understand. I'm not going to go through them here, but I am going to use a very straightforward technique, which is this backdoor adjustment. It's very straightforward when you know the graph, at least. And I'm just going to show you this is one possible way to recover the true effect of x naught on y. So the backdoor adjustment is simply about identifying the variables that can block the path, this backdoor path between the two variables of interest. So I've got this causal effect between x naught and y via x1 here, but I've got this indirect path here that's actually non-causal because this arrow is pointing into x0 that goes via x2 and x3. And this is what's known as a backdoor path. Information or statistical dependence, whatever you want to call it, can sort of flow, in inverted commas, through this backdoor path here. So the backdoor adjustment method is simply about identifying any variables that lie on this, that are sufficient to block these backdoor paths, essentially. So the backdoor sets in this graph are x2, x3, or both x2 and x3. So we can use either of any of these sets. They're all going to give us the same result. So let's just flip a coin. Let's pick x3 and run the regression. So we get y equals c, the intercept, plus a x0 plus b x3. And we get a perfect estimate of the causal effect of x naught on y here. Now, this is only possible because we understand what that graph is. We're only able to identify that backdoor set because we knew something about the true graph. And there are actually many algorithms that are being developed that help you discover these backdoor paths automatically. There's a lot of causal discovery algorithms, causal validation algorithms. And it's quite surprising to me that, given that we're scientists and we're really interested in answering causal questions, that there just is no use of these in empirical research. And obviously they're new and they're difficult to use, and they've got their own associated limitations and pitfalls. But I would hazard that these pitfalls are probably not as bad as having, you know, orders of magnitude incorrect inference when you don't consider these causal relationships. And there's an example here given in Brady Neal's introduction to causal inference talk, which was based on realistic data simulated. It was simulated so that we had the true effect here, which is 1.05, very simple graph. It was to do with blood pressure and protein in urine. And this was a treatment T and some outcome Y. And if we took a naive approach, similar to some of the approaches that we saw before, we actually got 400% error on the estimation for the relationship between these two variables. And if you start to consider the graph a little bit more, maybe you can reduce the error to say 20%, but if you actually get the causal structure right, you can work out the true effect 1.05. Now, the point to take away from this is I'm not necessarily telling you that you always have to use causal inference, and if you don't, it's all meaningless. I'm actually telling you probably something more scary than that even if you don't undertake causal inference, your results are probably still meaningless. If you're undertaking predictive research, all you're interested in is fitting this predictive model, you're not going to worry about all the assumptions associated with, you know, causality, ignorability, identifiability, and so on. You're just going to do predictive research. your coefficients are still meaningless, and you have to, be very careful about what those coefficients actually mean. It's all very well to do a predictive model, and all you're doing is just trying to predict some outcome, and you're not looking at the coefficients. But if you're actually looking at those coefficients in terms of their magnitude, their sign, their significance value, all those are associated with some kind of interpretation that you're doing, that takes these predictive model coefficients and tries to, infer something about what's actually going on in the world. And as we've seen, the amount of error on these coefficients can be absolutely astronomical. It would render your research completely meaningless. Just to sort of hit the nail in well and truly, I would imagine that there's many full professors that undertake research using these methods, for which their research is complete and utter waste of time. There is literally no point in getting this published. It is meaningless. So you can still use these coefficients to explain your model in some scenarios, but even that is risky. I don't have time to talk about explanation versus interpretation today. So actually that is pretty much what I wanted to say about causal inference. And in order to save time for questions, I'm just going to move on to the end here. I'm going to skip through the next few sections. See, I had to skip the section on cows and camels, which I was really looking forward to talking about. That was the highlight of the talk. This was to do with explanation and interpretation. But I'm going to skip to the sort of overall conclusions. This was more about explanation and interpretation. And I'm going to come back to the question in the title, which was prediction and causality, either, both, or neither. Well, in general, neither. Sad face, or sad vampire face. Unfortunately, I don't think people are really doing good predictive research. I don't think they're really doing good causal inference in psychology, at least. Now, in economics, they take causal inference very seriously. They've been a little bit slow on the uptake of machine learning models, but that is changing now. Chernyshkov is using machine learning and double machine learning for causal inference. But they may take upwards of 10 years to get a paper published. So they are really meticulous about whether or not their graph is going to be sufficient and their assumptions are going to hold, and that their causal inference is valid causal inference. So we have, it does require a little bit of a decision between undertaking a huge undertaking to actually discover the causal relationships between variables, do all the necessary work to validate that causal structure, to discover that causal structure, and then to answer a question at the end of it. There's no free lunch. I think the benefit of doing causal inference is that we can actually answer fundamental causal and scientific questions if we undertake that research properly. And if we're not doing that, if we're doing predictive research, we can do that a lot better than we are now, but we still have to understand that there's a fundamental gap. We are not going to be able to answer scientific questions with predictive models. So I'm going to go through my kind of synopsis from the paper. Researchers in psychology and social science lack some competence in the practice of prediction and causal inference. This is a bold claim, I realize. If researchers were more competent at prediction, they would, for a start, avoid interpreting linear model parameters using implicit causal language. So again, we've got a predictive model here. There's actually no interpretation that we can do. They're usually meaningless. They certainly don't correspond with anything external to the model, beyond, say, statistical associations. They're not scientific, they're not causal. And actually, it's a shame that people are still using causal language. They would avoid using naive linear models to test causal hypotheses derived from causal theories. So as scientists, we are, I understand, fundamentally concerned with causal theories and causal hypotheses, but the use of naive linear models like multiple linear regression results in misspecification, so you get wildly biased effects. We would be using varied and flexible functional approximation techniques and model explainability tools. I didn't talk about explainability tools, unfortunately, but essentially the message of this is that, if we were good at prediction, we'd be using machine learning algorithms. We would also be, straight on top of this necessity to use train test splits and cross-validation techniques. Could we leave one out, cross-validation? But this is, a real 101 for predictive techniques. We should be using it even if we're fitting linear models, whether or not we're doing predictive models or causal inference. And on the other hand, if researchers were more competent in causal inference, well, for a start, we'd be doing causal inference. I don't really see any causal inference in psychology, but we'd be less ambitious about specifying and interpreting large causal SEM graphs. So some of the SEM graphs that I see are very complicated, very ambitious, and none of them have been validated causally. They're just they're assumed a priori to be correct, and there's no validation of that graph beyond some predictive heuristic, like, oh, does it predict the outcome well? What's my R squared like? How much variance do I explain? Which again is the wrong approach. We can't use predictive heuristics to validate the causal structure of our models. We'd be more restrained when it comes to interpreting the coefficients of misspecified models. So rather than running, say, a linear regression and looking at the coefficients and saying, oh, this one's significant, that means this. This one's not significant, that means this. This one's large, this one's negative, this one's positive. They're all kind of they potentially be very, very misleading, especially if there's a compounding issue of limited functional form and causal misspecification. We'd be more transparent about the assumptions when defining causal models. So if we assume that people using SEM are actually trying to do causal inference, then they need to talk more about all the assumptions associated with that. So like identifiability, ignorability, unconfoundedness, positivity, all these assumptions that need to be sort of at least stated clearly. They would use more explicitly causal language and terminology. Obviously, at the moment, there's this weird conflated mix between the two. People don't seem to be clear about when they're using making a causal statement versus a predictive statement. And they would clearly distill and identify the specifics of their causal questions and hypotheses, and be less likely to worsen the bias and generalizability of their inferences by adopting ad hoc, data-driven model variable manipulation techniques during the analysis stage. So I have had the pleasure of working with psychologists that manipulate their SEM graphs until they achieve some desired level of significance or R squared. They may even, well, okay, let me leave what that one, that was too anecdotal perhaps. But essentially, the same considerations for predictive models apply to causal models. We need to be very careful not to overfit our models and to understand whether or not we're doing something that's based on a predictive heuristic that affects the causal structure of our model. Again, we saw how wild and varying those coefficients were if we misspecified a certain aspect of our model. It may come down to just the direction of one arrow in a large SEM graph, and it can have a huge impact on the meaningfulness of the results. Finally, if researchers had a clearer understanding about the differences between predictive and causal approaches, then we see more delineation between the two. I have a suspicion that the reason why we see so much conflation is partly due to the fact that people aren't clear on where the line is between a predictive model and a causal model. For a start, I said at the beginning, multiple linear regression itself is a causal model. And so we really need to get a feel and intuition for when one becomes another. I wanted to finish off to say this is not just psychology. It's in epidemiology, it's a huge problem, in medicine, in social science, in some of economics, and obviously psychology as well. But it's quite rife in the empirical sciences. One thing I haven't done yet that I want to really conclude with is to make some recommendations for improving practice, because I've been excessively negative so far. I made some bold claims that's going to step on lots of people's toes. I hope they have their bulletproof vest on. But let's see what we can do. So I think people, first of all, should really try their hardest to seek collaboration with experts in statistics, causal inference, and data science, and possibly machine learning. Modeling is very difficult. I've underlined practice here because the number of times I hear someone say, oh, I talked to my statistics friend and they said X or they said Y. And almost invariably, my impression has been that statistician has been wrong, at least wrong in relation to the specifics of the problem at hand. And I think there are a lot of statisticians that are very, very good at the theory behind their techniques, but there are other statisticians that spend more time practicing their techniques. So I think it's better to seek collaboration with people that have experience in the practice of these techniques. There's a lot of things that pop up in real world applications that perhaps aren't necessarily spoken about in a purely theoretical sense. I think it's important we're transparent and clearly articulate whether we're doing predictive or causal research. I would love to see less of this, one sentence it's causal, next sentence is associational, and it flips backwards and forwards. I would like psychologists to consider using predictive approaches more often. So this might sound strange because obviously I've said that causal inference just doesn't get used. So, surely people are using predictive approaches enough already. But again, I think I mean good predictive approaches here. So using predictive approaches that allow us to actually infer something more robust about the statistics underlying the data. And this is particularly useful during exploratory research, perhaps as part of validating causal relationships. But we still have to be very careful and understand that in many scenarios, this is going to be difficult to bridge that gap between prediction and causality. And finally, I think researchers should simplify, focus, and distill their research questions and hypotheses. So I think it's very good that we consider complex SEM graphs. I think that's important to have a sort of holistic understanding of all the things that have potential influence on the variables that we're looking at, but we need to really focus in on specific causal effects. And so if you look at, say, economics, they take 10 years to publish a paper and they're only looking at one path in that path diagram. They're not looking at estimating a whole SEM graph. And actually just estimating one causal effect is extremely challenging. And if we want to actually start producing sort of meaningful science and robust science and progressing the field, then I think we should shrink our ambitions a little bit and really focus in on answering the more fundamental questions. I think this is kind of clear when you think of the replicability crisis kind of undermined all of psychology 101. So, you know, if we have an opportunity to go back and answer these fundamental questions, then we should. And that can be quite unexciting because you want to make, you know, these bold claims and you want to answer everything all at once. But actually it's very hard. It's very, very challenging. So yeah, they're my recommendations. And I think we've just got a bit of time left for some questions. I hope I didn't put you all to sleep.
Right, thank you so much. A little clap for you. I keep forgetting to download this cheering sound online so I can play it at the end of the sessions that we have. I need to do it finally. But yeah, sorry, I'm just going to stop recording now so we can take the questions.